So we start with, you're welcome everyone. Thank you very much for making time to watch this video. This is the BG's Physics Classroom, and here we talk physics only. So your contributions are also welcomed. If you have any question, bothering your mind, you have any suggestion, any contribution in line with physics, don't hesitate to make a small video of yourself explaining or saying what you want to say, saying the question that you want us to deal with, and then you can either you can send it to the group BJ's Physics Classroom Facebook. The group's name is BJ's Physics Classroom, or you can write it on a sheet of paper and then post it there. I will allow it in both in the group and on the page for people to also have a look at what you have for the physics classroom and for all of us. Today's section of the physics classroom is going to be centered on Newton's laws of motion and linear momentum. This topic is intended for from friends in Form 1 that are at home. So stick and stay. I did this video some time ago, sometime in 2021, and then I decided to post it this time for people to have a look at it. So stick and stay and watch the video. Don't forget to subscribe to the YouTube channel, BJ's Physics Classroom, and also like the Facebook page, BJ's Physics Classroom. So all of them, BJ's Physics Classroom, BJ's Physics Classroom, like that. YouTube, the Facebook group, and the Facebook page, all of them, BJ's Physics Classroom. Subscribe and like the page, and let us move. Thank you. Watch the video. The Newton's laws of motion. So, Isaac Newton gave us 3 laws that govern motion. So we look at them one by one. Newton's first law of motion. The first law of motion, as propounded by Newton, states that a body at rest will continue to be at rest, or a body in a uniform motion will continue to be in the uniform motion unless it is acted upon by an external force. What is the meaning of this? So suppose let's look at this scenario. If I throw this object up, if I throw this, according to Newton's first law of motion, if I throw the pen up, the pen is supposed to continue to go up and not come down unless it is acted upon by an external force. So if this pen goes up and comes down, it means that a certain force is acted upon it, external force is acted upon it, and that is what is causing it to come to rest in space and then eventually coming down. That force is the force of gravity. So another interpretation of the Newton's first law, like I put this pen down here. According to the law, this pen is supposed to be here 100 years if no external force happens to it, if no external force is acted on it. And it is true. If no external force acts on this pen, the pen will continue to be here 100 years, which is true. So according to that law, we also call that law the law of inertia. So Newton's laws of motion. Newton's laws of motion. So we're dealing with the first law. Now, the first law, we also call it the law of inertia. So when we say inertia of a body, it is the reluctance, we define it as the reluctancy of a body to change its state. You can have state of rest, you can have state of uniform motion, state of time, state of direction. You have so many types of inertia, but at your level, you're only supposed to know inertia of time, inertia of rest, and inertia of uniform motion. So this pen is in a state of inertia, which is inertia of rest. So when I suddenly pull this one, the pen continues to be there. You understand that? Because the pen feels reluctant to change its state. So the pen is trying to obey the law of inertia. That's why when I pull the book, the pen continues to be there. That is the Newton's first law of motion. What are some of the applications of the Newton's first law of motion? Now, you see that passengers are provided with seat belts, or drivers are provided with seat belts when they are driving to wear. This is very important, my brother and sister. It's very important. The seat belt is there to protect you, the user of the car. The car can have an accident at any point in time. When an accident occurs and you are on your seat belt, if even the car somersaults, you will still continue to be at where you are until the car finally stops. Then you are safe. Yes. Then you are safe. So why the seat belt? Listen to this. Let's suppose that the car collides with another body. Or let's say you are in a car. The car hasn't collided yet. You are in a car. Then all of a sudden the driver applies the brakes of the car. Shoo, like that. So the car comes to a stop. But your body feels reluctant to change its state. What state was that? The state of uniform motion that the body was engaged in previously. When the car was in motion, your body was engaged in a state of uniform motion. So the body felt reluctant to change that state when the car suddenly comes to rest. So you realize that when the driver applies the brake, you are thrown forward because your body still wants to continue to be in that state. That is one of the applications of the Newton's first law of motion. So passengers in the car are provided with seatbelts so that when the car collides, you are not thrown forward. You are not thrown out of the car. If you don't take care and the car collides, you come out of the windscreen, and then the unfortunate may happen. God forbid that it happens. Good. So that is one application of Newton's first law of motion. Another application of the Newton's first law of motion is the fact that, when you are in a car and you throw an object outside the car, you throw an object outside through the window, the object hit the ground and ran and followed the car. You understand that? Because the car was in a state of the object was in a state of uniform motion whilst it was in the car. So when you throw it outside, when it hit the ground, it feels reluctant to change that state. So it will still have to continue in that uniform motion. You get the concept? Another application is what we call knee jerking or neck jerking. Sometimes, let's say you are watching TV, you are focused on a Chelsea match, and then all of a sudden your friend comes, because he knows that you are focused so much on the match, he will push in your leg like that. You call it knee jerking, or he'll push your back. When your back is suddenly pushed, you realize that your neck jerks out. That is very dangerous. It can cause your neck to break. It is because your body was in a state of rest before your body was pushed. So when your body is pushed or your knee is pushed like that, your head feels reluctant to change that state of rest. Your body is going. Your head feels reluctant to change that state of rest. So it still wants to continue to be there. So while your body is going, your head is not going. That is when you feel that your neck jerks. And that is very painful. So these are some of the applications of Newton's first law of motion. Good. We look at the Newton's second law of motion. Newton's second law of motion. The Newton's second law of motion. This law states that the rate of change of momentum of a body is proportional to the force applied to the body, and it takes place in the direction of the force. I'm taking it again. The rate of change of momentum of a body is proportional to the force applied, and it takes place in the direction of the force. So what is momentum? Momentum. We define momentum as the product of mass of a body and the velocity of the body. Momentum is the product of mass and velocity of the body. Anytime we multiply a mass by the velocity of the body, we get what we call momentum. So the rate of change of momentum, according to the second law, the Newton's second law, which gave rise to the formula for finding the force, which gave rise to the formula for finding net force or force, the Newton's second law is interpreted as this, that the force applied is proportional to the rate of change of momentum. Change in momentum, rate of change of momentum means change in momentum per time taken. So momentum, mv minus mu all over t. The u stands for the initial velocity. So we'll multiply the initial velocity by the mass. That will give us the initial momentum. We'll multiply the final velocity by the mass. That will give us the final momentum. So mv minus mu all over t is proportional to F. So when we remove this proportionalities, I will introduce a constant. F is equal to a constant K into bracket mv minus mu all over t. But this constant K was found by Newton to be 1. Because you know that 1 Newton is equal to 1 kilogram per meter squared. So for that matter, this constant K is equal to 1. Therefore, F is equal to mv minus mu all over t. This is the formula for force. Why? Let us, we have dealt with linear motion, so we know this. Let us factorize m out. If we factorize m out in this equation, let me write it here, we'll get this. F is equal to m into bracket v minus u all over t. Look at this. V minus u all over t. That is acceleration, right? Yes. That's acceleration. So in place of this, I can put acceleration there, and that will give me F is equal to ma. So from the Newton's second law of motion, we get the force F is equal to ma, which we refer to as net force on a body. Good. So this is what we deduced from the Newton's second law of motion. Applications of the Newton's second law of motion. If you haven't been to the stadium before, well, one day you go there. When you go there, observe this. High jumpers and pole vaulters are given foam mattress to land on. All right, they are given mattress to land on. Why? Because this high jumper jump into space. He's fallen under the force of gravity, so his velocity is increasing as he gets to the ground. This high jumper is going to hit the ground with a certain initial velocity, which is huge. The moment he hit the ground will not move, so his final velocity will become 0. What that means is that when the final velocity becomes 0, the change in momentum is going to become minus mu over t, which will produce the force in opposite direction because the change in momentum is negative now. So that will produce a force in opposite direction. Remember, in the Newton's second law of motion, the change in momentum must take place in the direction of the force. So if I write mv here, the change in momentum takes place in the direction of the force. So the force is positive, the change in momentum is positive. They are in the same direction. But in a situation whereby the change in momentum is negative, that is the situation of the high jumper that jumps and hits the ground, his momentum comes to 0 at once. And the force is in opposite direction, which is acted on the person that is hitting the ground. So because it takes small time for his momentum to change, why? Because he hit the ground, bang! It takes a very minute second for his momentum to change for his momentum to change. That small second will produce a very large force because the force is inversely proportional to the time. So that small time will produce a very large force which is acted back on him, and that causes him to sustain damage, to sustain injury. So in order for the high jumper or the pole vaulter not to sustain injury, what the athletes, the organizers do is that they provide this gentleman or this lady with a foam mattress, thick one like that, for him to land on. So when he lands on the mattress, it will take some time for the momentum to change. So the mattress will surge in and come out. And it will do that about 3 times. So whilst that is done, it is buying time for the momentum to change. Yes, even though the momentum will finally come to 0, yes. But because the time taken for the momentum to come to 0 is huge, what that means, the force acting on him is less, it's very small. So when he hit the mattress, he will feel that yes, he has slammed it. But the force acting on him is not huge enough to cause damage to him. This is the reason why high jumpers and pole vaulters are provided with mattress to land on, because of the Newton's second law of motion. Else, death. Another application is, let's look at a car that collides with a tree. Of course, trees are stationary, you know. Good. So a car that collides with a tree. Let's compare that one with a car that hits a wall. The wall breaks and the car enters. Which of these two cars will sustain damage? Of course, it is the car that hits the tree. Why? The tree is standing. The car bumps into the tree. Bang! It takes a very small second for the momentum of the car to change from that huge velocity to 0. So the impact on the car, because of that small time it takes for the momentum to change, the impact on the car is very huge. That caused the car to sustain much damage. Let's look at the other scenario. A car that hit a wall, the wall breaks. So the car hit the wall breaks, then the car moves small and then goes to stop. The car took some time for the momentum to change, to come back to 0. Because the car took some time, and the time is in proportion to the force that is acting on the car becomes less small. And the car does not sustain much damage. You get the principle? Good. The car does not sustain much damage. So these are some of the applications of the Newton's second law of motion. You know? Good. Let's end it there. There are so many examples that we can talk about, so many applications. Let's look at the Newton's third law of motion. The Newton's third law of motion. So the third law of motion. What does the Newton's third law of motion say? It states that to every action there is equal but opposite reaction. To every action there is equal but opposite reaction. What is the meaning of this? To every action there is equal but opposite reaction. Remember, the action and the reaction, they occur simultaneously. So once there is the action also takes place. You understand that? So if the action will have to take place, then later the reaction will come and take place. It wouldn't satisfy the Newton's law. For instance, somebody slaps me. Then I go and think about it. It pains me. At that point, it didn't pain me like that, but I go and walk around, then later it pains me, then I come back and slap the person. That is not action and reaction. Are equal and opposite? No. The action didn't occur simultaneously. You understand what I'm saying? One of them happened, it took some time, then the other one happened. There was a thought through. That is not action and reaction being equal and opposite. A typical application or example of it is the firing of a gun. You see, when a gun is fired, let me use this thermometer as an example. When a gun is fired, the bullet moves out with a very high speed. The bullet's speed, very high, multiplied by the mass, will give the bullet a certain momentum. The emphasis on the momentum, not the speed. Take note of it. That will give the bullet very high momentum to go. That is the action. According to the law, there has to be equal but opposite reaction. So the gun recoils backwards. Alright? The gun recoils backwards. So the recoiling of the gun with a small velocity. Why small velocity? Because the gun has a large mass. So the large mass of the gun multiplied by the small velocity will be equal to the high velocity of the bullet multiplied by the small mass of the bullet. I think it makes sense, right? That is the reason why you don't have to use the velocity to explain it, but you have to use the mass. Sorry, the momentum to explain it. So what is the action here? The action is the bullet moving forward with a momentum that will produce equal but opposite momentum backwards, which is the gun recoiling. Another practical example is the firing of a rocket. You know, when a rocket is fired, a large mass of smoke comes out with very high speed. So that large mass of smoke coming out, which is the action, produces equal but opposite reaction. It produces equal but opposite reaction, which propels the rocket forward with very high speed. So the rocket being propelled forward is the reaction. The smoke coming out of the gun, coming out of the exhaust of the nozzle of the jet or the rocket is the action. Another practical example is the paddling of canoe. You know, when you paddle a canoe, you sweep the water out like that. Action. Equal but opposite reaction. The canoe moves forward. So action, reaction. Action, reaction. The two of them happen the same way. Whilst you sweep the water backwards, the canoe also move forward. It's not that you sweep the water backward, then later the canoe move. The two of them happen simultaneously. I hope that is clear. Good. So these are the Newton's 3 laws of motion and the applications of the 3 laws of motion. Okay, so thank you for making time to watch this section of the BJ's Physics Classroom. The next episode of the Newton's laws of motion and linear momentum will come your way on Saturday, this coming Saturday. I think that will be 2nd of July. Yes, this Saturday, 2nd of July 2022. So watch out for the 2nd episode, you know. So I'm going to be releasing 2 videos a week until the topic is done, then we'll move on to another topic. So thank you very much for watching us, and don't forget to subscribe to the YouTube channel and like the Facebook page. Please share the video so that others may also get it. Thank you. Bye-bye.